All right, everybody, welcome to the video here for lesson number 11, where we're going to do more modeling with exponential functions. So in lesson number 10, we learned how to model exponential functions with, exponential decay and growth. We talked about half-lives. And in today's lesson, we're going to use those same concepts and those same equations, but kind of make the word problems a bit more challenging. So just a little bit more wordy. That's all we're really doing here. So in the opening exercise, it says the number of bacteria in a petri dish after t hours is modeled by the function p of t. Now there are three numbers in this function, 75, 3, and 2. And we want to know, what does each number mean? So 75 is the initial value. All right, so that's the initial amount of bacteria, because it's being multiplied to whatever this is causing the rate to increase or decrease. The three is telling us how the function's increasing. I know it's increasing because the number is more than 1, and it's increasing by 3 times the amount. So similar to Half-Life formula, where that number was a half, and every certain amount of hours or days or whatever, it got cut in half. Well, since this base number is 3, it's going to become 3 times the size. So what we can say is the bacteria is growing 3 times the size. Now, it's kind of like a half-life, but it's each amount of time, all right? So what is that amount of time? So that's the 2. All right, so since the denominator of the exponent is 2, we can say the 2 represents the time for the bacteria to triple. Now, you might be looking at this and saying, well, why isn't the base 1 plus r? And the reason why is the exponent's not just t. So if I kind of do some exponential work there, I can make it so that the exponent's t and determine what the effective rate is, but that's not what this question is asking. All right, so let's look at number 1. So it says the number of organisms increased 50% every 4 minutes. There were initial 30 organisms at 1 p.m. Write a function for the amount of organisms after t minutes after 1 p.m. So a of t, we have our initial amount of 30, and the exponent is going to be t over 4. We need to figure out what goes in that parenthesis. So in the previous lesson, we learned that we put a half there if it's half the amount of organisms after 4 minutes, but this is getting bigger, so this has to be more than 1. So since it's 50% more, it's 1.5%, or 1.5 is the base, sorry. So it says use your function to determine how many organisms there are at 2:15. So if the starting time is 1 and we want to go to 2:15, that's 1 hour and 15 minutes. But notice the function is in minutes. So I have to make this 75 minutes. I know that because each hour is 60 minutes. So I can say, what is a of 75? And then I just have to type that in my calculator. So if we type that in real quick, I get a ton of organisms, because it's tripling every 4 minutes, and that's 75 minutes, so this is going to be a lot of organisms. It's exponential growth, so remember, these numbers are going to get bigger really quickly. And since we're talking about organisms, we can't have 0.17 of an organism, so we're going to say it is going to be roughly 60,074 organisms. Then it says, what is the percent of increase of organisms in terms of every minute? So that's asking us to rewrite this equation here, but make the exponent just t. So if I rewrite that, we have a of t is equal to 30 times 1.5 to the 1/4 exponent all to the t. So we're making it so that the equation is in terms of minutes instead of minutes over 4. So now I just got to clean that up a little bit. 1.5 to the 1/4 power becomes a decimal. Remember, these are going to be messy decimals, so just round out to 4 decimal places, usually good enough. where t represents minutes. Now it wants us to find a percent increase. So I know this represents 1 plus r. So if I subtract 1 from that, I get a rate or a percent of increase of 0.1067. Show that as a percent, 10.67% every minute. So every minute, this amount of organisms is going up almost 11%, which is why it got so big so quickly. All right, let's keep going. So we have another one of these Half-Life questions. So it talks about this iodine 131. Remember, whatever this is, don't let the chemistry part confuse you here. It doesn't matter, right? We're just talking about half-life. We know the generic half-life formula. So it says a patient was given 20 milligrams. That's the initial amount. So we have I of t is equal to 20 milligrams. It's a half-life, so the base is a half. And it says that every 8.2 days, this is going to decrease by half. So that's my number in the base of the exponent's fraction, or the denominator of the exponent's fraction. So then it says determine the daily percent decrease. So since t represents days, I want to make it so that the exponent is just t. So just like I did in the previous question, I need to use my exponent rules here and make this 1/2 to the 1 over 0.82 all to the t, so that that exponent is just days. Again, just like it did previously, clean it up a little bit. So we have I of t is equal to 20 times 0.9172. Now, this right here represents 1 minus the daily percent decrease. So if I want to figure out what r is, I got to do some math here, right? So I got to figure out how far is this 0.19972 number from 1. So if I do 1 minus 0.9172, I get a rate of 0.0828, or about 8.28% per day. So what that's saying is every day this value goes down about 8%. All right, let's keep going. Number 3 says, assume the population of deer in Argent County is growing at a rate of 16% per year. Currently, there's this much deer in the county. Write a function d of t. So since this is per year, right, I know I'm going to use the formula of the future value is equal to the initial value, 1 plus the yearly rate, all to the number of years. So we'll say d of t is equal to the initial value of deer, 1 plus the yearly rate, all to the t. So I can rewrite that. Again, we just want to clean up that fraction, that parenthesis, and we are all good. Now it says write this function in terms of the monthly growth rate. Well, if t represents years, and I want to write that as months, I need to take the number of years and make it so that I can represent that as months. So if t is years, I could say 12 times t is equal to months. So I can rewrite this by saying d of t is equal to that still initial amount times some number all to the 12t. Now, what do I put in here? Well, since I raised the exterior exponent to 12, I have to raise the interior exponent to 1 over 12. Because if I was to use the power to power rule, that 1/12 times 12 becomes back 1. So that's all good. So we've really not changed anything, just what it looked like. So now I can say d of t is equal to 11,750 times whatever that is, 1.16 to the 1/12th power. So that gives us 1.0124 to the 12t. So now this is in terms of the monthly growth rate instead of the yearly growth rate. So I could take this number down here, 1 plus r, and I can say the monthly growth rate is 0.0124, which is about 1.24%. That's all we're doing, right? We're just changing the exponents around so that we could change the rate. That's it. Keep going. Last twist on exponents. So this next problem is kind of tough. So it says Seth invests $4,500 in an account, which is compounded annually. So I know that's the future value is equal to the initial value, 1 plus r all to the t. 3 years later, Seth's account is $5,091.50 without having to make any deposits or withdrawals. Determine the annual growth rate. So here, we're going to have a little bit more math to do because the unknown is not going to be the ending value or the principal value or the t value. It's going to be the rate. It's going to be the variable inside the parenthesis. So let's use what we know. So we know the ending amount or the future amount. We know the initial amount. We don't know the rate, but we do know the time. It says 3 years. Algebra, right? Divide away the 4,500, get what we're trying to solve for isolated. Now, I'm not going to type that in my calculator because I'm going to assume it's going to be a very messy decimal. And I don't want to round it yet because if I start rounding now, it's going to be bad. So I want to get rid of the exponent of 3. I could do one of two things. I could take the cube root of both sides, or now that I know a little bit more about exponents, I could say, well, instead of doing the cube root to both sides, I could raise this to the 1/3 power. Whatever I do to one side, I do to the other. 3 times 1/3 cancels. So now I'm left with this messy fraction to the 1/3 power, which now I could type in my calculator. So use a parenthesis here, so do 5091.15 divided by 4,500, and raise that to the 1/3 exponent. And that gives us 1.04200 equals 1 plus r, subtract 1, and now I have my r is 0.0420. So now I can figure out the yearly percent rate to nearest tenth is 4.2%. How did I get that? I just moved my decimal twice. Now, do you have to use fractional or rational exponents to do this? The answer is no. But sometimes you don't want to take like the 15th root or something weird like that. So using the fractional exponents actually make this a little bit easier to type in your calculator. Let's try another one. So it says in a small city you have a population of 200,000. 5 years later, there's 235,000 people. Assuming the population grows exponentially, compute the growth rate to nearest tenth of a percent. So again, this is a yearly rate, so it's the same formula. Future value, the initial value, 1 plus that rate that we don't know, all to the 5th power. So again, we're going to divide away the 200,000. If you're good with numbers, you know those zeros are going to cancel. So we could even simplify that one, because that's probably going to be a nice number. 1.175. The last one I didn't simplify here because that definitely is not going to be a nice number, right? But that one's a decent enough fraction or decimal to use. And we have 1 plus r all to the 5th power. So again, here's a good example of why using radicals here is not really the best method, because I don't want to type in the 5th root. I'm just going to do 1/5 exponents. Exponents are usually easier, right? I say it in class all the time, fractions are your friends. Here's an example where fractions are your friends. Makes this easier. So if I do 1.175 to the 1/5 power, I get 1.03278 equals 1 plus r, subtract 1, and we get 0.03278 equals the rate. There's tenth of a percent, so that'll be 3.3%. All right, moving on to the homework, all right? So number 1 says the debt is growing at a rate, annual rate of 3.5%. What's the percent for it growing per month? So if I take the yearly rate and add it to 1, that's going to be to the number of years. If I want to change that to months, I would do 1/12 inside and 12 times the number of years on the outside. So now I just have to type that part on the inside of the fraction in my calculator to make it look nicer. So that's the same thing as me saying 1.0029 to the 12y. Remember, 12y represents the number of months. That's why it's the monthly rate. So what is the monthly rate? It's 0.29%. Number 4, a population of a town is decreasing by 4% every 5 years and started with 12,500 residents. Create a model and use the data to predict the number of people in 10 years. State the yearly percent of increase. So it says a population decreasing by 4% every 5 years. Well, that's a little bit different, right? So we got to take that into consideration. So here's our model. So we'll say population is 12,500. It's decreasing, right? So we want to go 1 minus 0.04. But this is every 5 years. So we have to represent our exponent in terms of years, but every 5th year. So if we have the number of years, hold on 1 second. Sorry, I heard my daughter in the other room. All right, so we want to make this happen every 5 years. So we're going to take the number of total years and divide it by 5. Similar to how we do half-lives, where we're saying over a course of the number of days or months or years, something is going to divide by 2. I'm saying over the course of 5 years, this is going to decrease by 4%. All right, so if we predict after 10 years, plug in 10, clean up the middle, we can predict the number of people in 10 years. Remember, we're talking about people here. So when we round this, we want to make sure that we round it in a way where we are going to have a whole number. Luckily, no rounding necessary. Oh, I did divide. I knew that did not seem right. I hit the wrong button. Hold on 1 sec. That makes more sense. 11,520. All right. Number 3, a payday loan company takes a loan of $100 or $1,000 available to customers. Every 14 days, customers are charged 30% interest on compounding. In 2013, Rummy took out a $300 payday loan, create an exponential model for P of T to show the amount they would owe after T days. Hold on 1 second. My wife is calling. All right, so back at it. Sorry about that. All right, so because we have this payday between $100 and $1,000, that first sentence really doesn't matter too much because the number that we were given is between that much. So if we're trying to figure out an exponential model that we can use here, so we have our initial amount. It's going up by 30%, so that's 1.3 as my base. Where did I get 1.3? 1 plus 0.30 is 1.3. And then the exponent, right? The exponent is going to be the number of days that they have this, so t, divided by 14, because that's when it's compounding. It's compounding every 14 days. And it doesn't ask us to do anything else, so that's it. We're done. Moving on. All right, so create an exponential model for 100 grams of strontium-90, which has a half-life of 29 years. Determine all of your variables. Create an equivalent equation to highlight the yearly rate of decay. So let's first make this model for the half-life. So we have this model, whatever variable we want. So we'll call this S for strontium, S of T. And we have 100 as my initial sample, half-life, and it's going to be the number of years divided by 29. Now that's our initial expression. So determine all your variables. So here's you have your initial amount, right? Here's your half-life, right? So that's your rate. And 29 years is the amount of time it takes for a half-life. Now, if we want to rewrite this to highlight the yearly rate of decay, we want to make the exponent just t. So I'm going to rewrite this as S of t with 100 we have 1/2 to the 1 over 29 all to the t. That's highlighting the yearly rate. So then the yearly rate is whatever that parenthesis comes out to be. So if I do 1/2 to the 1 over 29, we get 0.9764. Meaning, if we do 1 minus r is equal to that decimal, the rate is whatever that comes out to be. So my rate is going to be 0.0236, or about 2.36% per year. Lastly, so $5,000 invested in an account compounds quarterly. Determine the annual interest rate for the account after 5 years when the account is $5,805.92. So again, this is going to be one of those weird questions where we have to find the rate. So if we plug in what we know, so we know the ending amount or the final amount, future amount, whatever you want to call it. We know the initial amount. We know it's 1 plus the rate, which we don't know, divided by quarterly. So that's 4 times a year, all to the 4 times 5. Divide by 5,000. Don't type that in your calculator. That's a messy decimal. So we'll leave that 5805.92 over 5,000 is equal to 1 plus r over 4 all to the 20th. I want to get rid of the 20, so I'm going to raise both sides of this to 1 over 20. Those 20s cancel. So now we're talking about this decimal all to the 1/20th, so let's type that in. Parentheses, 5805.92 divided by 5,000 all to the 1 over 20th. So that's 1.00749 ... Leave that decimal in your calculator for a minute. Subtract 1. So in your calculator, just hit -1, and you get 0.07499 ... equals r over 4. And I multiply both sides by 4. Again, leaving that decimal right in your calculator. Now just hit times 4. Right? This way we're not actually rounding. So we'd see we get 0.02999 ... equals the rate, which we can change to a roughly 3%. All right, so we have a 3% increase every quarter. All right, it's going to be 2.999, so we could say 3%. That's it. Hopefully that lesson helped you. Make sure you keep watching these videos. If you missed something, you were absent for a day, just go back a couple lessons, rewatch them, right? Because we are getting really close to the end of the chapter. We have one lesson left before we start preparing for our test. All right, so best of luck, and I will see you all soon.